In Unit 3, we're looking at polynomial and rational functions. Specifically, we're going to start out with quadratic functions in this first video. Here, we want to recognize the characteristics of a parabola, graph parabolas, and determine and solve problems involving the minimum and maximum value of a quadratic function. We have to start with what a quadratic function is to be able to talk about quadratic functions. Any function of the form f of x equals ax squared plus bx plus c is a quadratic function. If you recall, we've heard that word quadratic before when we were talking about quadratic equations. Notice that they look very similar to a quadratic function. It was basically a quadratic function set equal to 0. It was the definition of a quadratic equation. So hopefully that's not a surprise to you. We can use completing the square to rewrite this in this, what we would call standard form of the quadratic function. Let's try that here. Let's start with f of x equals 3x squared plus 12x minus 6. Notice that this is a function here, so it's not an equation, so we're limited on what we can do to it. We can't add and subtract things. We have to be really careful because we still want that function notation on the left side there. We do know that we have to factor out the 3, at least out of these first two terms. I'm going to leave a little bit of space if we want to complete the square. Because remember, from completing the square, we had to have a 1 in front of the x squared as our coefficient on the x squared. Let's take a look here. If you recall, we took the b, which in this case is 4 after the 3 is factored out, divide it by 2, and then square that whole thing. And you get 4. 2 squared, 4. We're going to add 4. When we completed the square for solving a quadratic equation, I think we just added 4 to the other side of the equation. But this isn't an equation, so we can't just add 4 to the other side. So instead of adding 4 to the other side of the equation, we're going to subtract 4, and that still keeps it balanced, right? That is still equivalent to what we started with. I'm going to rewrite this as 3 times x squared plus 4x plus 4. I'm going to bring that minus 4 out of the parentheses because I don't really want it in there. When I do that, I have to bring it out as 12 because we have to consider both this and this are multiplied together, right? That's where we get this minus 12 from. I'm going to factor this x squared plus 4x plus 4. That's our perfect square trinomial. So now we have rewritten f of x as 3 times x plus 2 squared minus 18. That is the form we were looking for, where a is 3, h is negative 2, and k is negative 18. You might ask, why do we care? Why would we want to do that? Why would we put ourselves through completing the square, which is super fun? I know most of you think that. So why would we do that? Well, the reason is that it can tell us something about the graph of a quadratic function. Let's think about what we know about that. If you recall, this is a transformation of y equals x squared, the standard parabola that we looked at when we talked about transformations of functions in Unit 2. So because of that, we know that we're going to have possibly a stretch or shrink here with that A. This is a left or right shift, and that's an up or down shift. So that's why we're excited to rewrite that quadratic function in that different form, because now we know that every quadratic function is a parabola. And this picture over here is just kind of funny, right? This one's shifted right and down. This one's the parent function, the standard function. This one's shifted just right. This one's reflected, maybe shifted down a little bit, right? So we definitely, because we can always write a quadratic function as in this standard form, we know that we're always going to get a parabola that is somehow transformed around the plane. Sometimes students, usually students, always you should be asking, why do I care, right? Why do I care about parabolas? Well, we have a lot of physical applications of parabolas. One of them is if you throw a ball up in the air, it will follow a parabolic path. Really anything in the air will follow a parabolic path, unless it's got, you know, a air resistance issue that it is having a bigger issue. If you throw a feather in the air, it's not going to follow a parabolic path because there's, you know, other things at play there. But here's another example. A swim team member performs a dive from a 14-foot high springboard. The parabola below shows the path of her dive. So when the diver dives from the board, they're going to have some sort of parabolic shape. And it's because of the way that gravity works on objects that are unaffected by other things. That's just a couple of examples. We'll come back to some applications and see how we're going to use that towards the end of this video. We know that all quadratic functions are parabolas. Let's describe how we graph them. All right, so we're going to look at a couple of things. First of all, the opening A. If A is positive, we know that that function will open up, that parabola will open up because there's no reflection there, right? If the A was negative, you would have a reflection and it would open down. Whichever form you're in, remember this A and this A are going to match because of the way that you factor that out to complete the square, right? Let's go back up here for a second where we actually did that. The 3 here matched the 3 here because we factored that out. So that will always be the same A there. That's why we use the same letter. The H and the K are different than the B and the C. This parabola opens down because f of x equals -2 times the quantity x minus 4 squared plus 8. That -2 tells us we have a reflection of that parabola over the x-axis. The vertex of the parabola is it's the bottommost point if the parabola opens up, and it is the topmost point if the parabola opens down. So we're talking about if you have a parabola that opens up like this, we're talking about this point right here. And if it opens this way, we're talking about this point right here. Okay? This would be the minimum of the function, and this would be the maximum of the function. When you are in this standard form after the completing the square, the vertex is the ordered pair HK. The reason for that is because that is a right shift, the H is, so the vertex moves to the right from the origin, and the K is the up or down shift, so that moves it up and down. It's a little more complicated when you're in the other form. it is negative b over 2a is the x value. So you're going to take the opposite of this number and divide it by 2 times that number. That gives you the x coordinate. I love sharing an office with my husband. His phone's ringing. He's walking into doors. Oh, it's super great.
Sorry.
No problem. So that's the x coordinate of the parabola. The y coordinate of any function we find by plugging that x coordinate into the function, right? The corresponding y that goes with that x. So that'll help us find our vertex when we are in that standard form. Parabolas have symmetry over the axis of symmetry. That's going to be this line that goes through the vertex, the vertical line that goes through the vertex. Let's look at that same function that we looked at above. The vertex of this is going to be 4, 8. If you look up here, inside, when it's in this standard form with the completed square there, the h is 4, the k is 8. So that's our vertex there. Let's take a look at this one. This is in the other form, right? A equals 4, b equals negative 8, c equals 3. If we use this formula above, negative b over 2a is going to be the h, or the x coordinate of the vertex. That's typically what we use, is h k to represent the vertex. So h is negative b over 2a, and k is f of that. Negative b, opposite of b, will be positive 8 over 2 times 4. Oh, that will be 1. To find the k, we take that x value and plug it into the function. Oh, I made a mistake here. It's not f. The name of this function is g, right? So 4 times 1 squared minus 8 times 1 plus 3 will be 4 minus 8 plus 3, which is negative 1. So the vertex is 1, negative 1 for this parabola. It's obviously easier to find the vertex when it's in the first form here, this in part A. So it's up to you if you prefer. You can complete the square to read the vertex off, or you can use this formula. It doesn't matter to me. We're trying to find out all this information about parabolas, right? And so we want to know which way it opens. That's a big helpful thing to know. We obviously need to know the vertex. Here's the problem with if you just tried to start plugging in values to try to find where this parabola is, you're never going to know where that vertex is. And so say, for example, on this one where the vertex is 4, 8, let's suppose you did a table of values, and it's pretty common to do something like this. You're only going to get half of that parabola, right? If you do this table of values, and not even half of it. You're going to get, just a portion of that parabola. That's really not helpful. It's critical that you know the vertex of a parabola to really know what it looks like. The intercepts can also help you get a good idea of the width. Remember that stretch factor that could happen, either stretching or shrinking horizontally or vertically. I actually don't worry too much about that, because if you have the intercepts, if it is a parabola that has intercepts, then you get a lot of information. So you don't really necessarily need to worry about that stretching. I think that's the hardest part about transformations of functions. And so if you can sort of avoid that by using another tool, then I would recommend you do so. And that's what I do, at least I try on a parabola. And I'll tell you what I mean by that. The y-intercept, we've talked about intercepts before. The y-intercept always comes from setting x equal to 0. There will always only be one y-intercept. Why is that? I want y'all to have an answer formulated in your brain. There's only one y-intercept because it's a function. So you can't have 2 points on the y-axis. Otherwise, it wouldn't pass the vertical line test. You'd have x equals 0 corresponding to 2 different y values, and that's not okay. It just doesn't happen with a function. Okay, let's talk about the x-intercepts. Same rule we've had before. You set y equal to 0 and solve for x. That's where those tools for solving quadratic equations that we saw in the very first unit will come in handy, because you'll now have a quadratic function set equal to 0, which is a quadratic equation. One thing that's important about the intercepts, you could have no x-intercepts. That's this first picture where it doesn't cross the x-axis. You could have one x-intercept where it's right, where the vertex is that x-intercept, where it's right on the x-axis. Or you could have two x-intercepts where, say, in this case, it's shifted down and it crosses the x-axis in 2 places. This exact same picture could happen if your parabola is opened down, right? If they were just reflected over the x-axis, you still have the exact same picture, whether it opens up or down. Okay, this says find all intercepts of this function. This is that same function we've been looking at. We already talked about how it opens down and its vertex is at 4, 8. The y-intercept, let's start with that. Plug in x equals 0. We get -2 times, that'll be 16, plus 8, -32 plus 8. Oh, this is kind of a tough one. -24. So my y-intercept is the ordered pair 0, -24. I prefer that you write intercepts as ordered pairs. That's what they really are. They're points in the coordinate plane. So they need an x value and a y value. A lot of online homework systems that you'll be working in just require that you put the y value, the -24. I'm not a big fan of that, but just so you're aware, just follow the directions, whatever it says there. Okay, the x-intercept, remember, is where x-intercept or intercepts is where y equals 0. So we set this function equal to 0. I'm going to subtract the 8 over, oops, I forgot my square there. I know a lot of times we want the function set equal to 0, but in this case, I want to use the square root property. So I am going to get that quantity squared by itself. Here I get 4. Square root both sides of this. When I do that, I have to remember my plus minus. And then I get x minus 4 is plus or minus 2. X minus 4 is 2, gives me x equals 6. X minus 4 equaling -2 gives me 2. So my x-intercepts are 6, 0, and 2, 0. I want to go back to that idea that I was talking about with stretching and shrinking and not necessarily always needing to do that. Here you would have to double all the y values, right, because of that stretch factor. But if you think about plotting these points, you now know this function opens down. You know the vertex. You know the x-intercepts, and you know a y-intercept. That'll give you a pretty good gauge of the width of this function. You've got quite a few points there. So I don't think you need to necessarily worry about that stretch factor. I do want you to be thinking about the fact, though, that multiplying all the y values by 2 makes those numbers get super big, and so the parabola gets narrower. That's why this, being such a hugely negative number, isn't really a surprise to us, because that stretch factor there. We are asked to actually graph this now. I'm going to bring all of our information over. that we already figured out for this parabola. We figured out that it opened down. If you scroll up, you would look that we found the vertex to be 4, 8. We said that the y-intercept was 0, negative 24, and the x-intercepts were 2, 0, and 6, 0, right? Yeah. 2, 0, and 6, 0. Okay. I'm going to go ahead and plot the vertex. I think what I want to do I want to make the scale on the y-axis go by 2's. I'm still going to leave the x-axis scale of 1. At the y-axis, I'm going to let the scale equal 2. So this is 2, 4, 6, 8, 10, and so on. That means my vertex, 1, 2, 3, 4, 8, is here. It opens down, so I should expect everything below it, all the points to be below it, because when it opens down, you have that maximum, that highest point. Let's graph the x-intercepts. 2, 3, 4. Just remembering that this scale is by 1s, so I'm going to have an x-intercept here and here. 2, 0, and 6, 0. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Oh, shoot. I thought I was going to have enough space. My y-intercept would actually be down here off the chart. I thought I was going to get there. I thought I had 12 boxes there. So 0, negative 24 is down here. If you are using ALEX for your homework, which if you are my student, you are, and several other classes, that program will ask you to graph the vertex, and then it'll ask you to graph 2 points on either side of the vertex. You have 1 point on either side of the vertex, in this case, with the x-intercepts. You have another point on the left side of the vertex with the y-intercept here, but you need another point on the right side of the vertex to satisfy what it's asking for there. I use symmetry for this. So remember that we have symmetry through the vertex. That means this point that was down here at 0, negative 24 is going to have a symmetric point at the same y value, and we have to figure out what x value would be symmetric to that. It is a distance of 1, 2, 3, 4 from the y-axis to that axis of symmetry. So we need to go 4 the other way. 1, 2, 3, 4. That's going to take me out to an x value of 8. The vertex is right in the middle there. Notice also that the x value of the vertex is right in the middle of these x-intercepts because of the symmetry of those. So we use this, we graph this, connect the dots. There we go. All right. Let's take a look at this one. I believe this is the same one that we did before, that we found the vertex of before. This opens up because that number is positive, that 4 is positive. Let me just double check and make sure this is the same one we did up here. 4x squared minus 8x plus 3. Yes, it is. And we found the vertex up there. Shoot, it was 1, negative 1, right? We have not found any intercepts of this, so let's do that. The y-intercept, we're going to find a g of 0. 4 times 0 squared minus 8 times 0 plus 3. In this form, all of those go away, and it's just that constant on the end. So there's your y-intercept. Talk about x-intercepts. 0 equals 4x squared minus 8x plus 3. I'm going to go ahead and plot these points. 1, -1, 0, 3. 1, 2, 3. By symmetry, I know I'm going to have another point here. That symmetric point is going to be, because my vertex was at 1, I'm going to go over to 2, 3, the same distance along the x, same y value. These x-intercepts are going to be somewhere between 0 and 1 and somewhere between 1 and 2 for this graph to actually work, right? Like we got to hit the x-axis. It's pretty narrow because that 4 is a stretch that makes it really narrow. I'm going to use the quadratic formula here. I think that's the easiest way to, because I know those aren't going to be, oh shoot, that's a terrible picture. I know those aren't going to be integers. They're not going to be nice, pretty numbers because they have to be between 0 and 1 there, and between 1 and 2. So we'll do opposite of b, plus or minus b squared will be 64 minus 4ac all over 2a. So we get 8 plus or minus the square root of 64 minus 48 over 8. 4 times 12. 8 plus or minus the square root of 16 over 8. Interesting. I was not expecting that. 8 plus or minus 4 over 8. 12 over 8 or 4 over 8. So we have 1 1/2, 3/2, or 1/2. They're right in the middle of those. Right there in the middle. This picture is not a great one. Let me try and start over here. It's hard to be particular here. -1, 1 is here. 0, 3 is that one. And then these are at 1/2 and 1 1/2. So I have this picture for this parabola. Super narrow. Oops, I missed that spot, but you get the idea. Super narrow because of that 4, how much of a stretch factor that is. And another important part of quadratic functions is the concept of the minimum and maximum. There's enough in that we need to talk about. I got to show you how to do it on a calculator and so on, that I want to unpack that really, really well. And I don't want to make this video excessively long. So I'm going to do that in another video. So look for that to come in another video.